say, ah yes, the reason there's more data held in IMS is because it's been running longer, whereas DB2 is more recent. So that's another theme of the 60s. Another theme of the 60s, which we won't spend much time on, I've called total and addabas, because there's interesting things about total and addabas. Total came first, and in my view, total is the more interesting of the two, for reasons I'll talk about later. This was produced by Syncom. I think the first release was 68, but give or take later. But the interesting thing about those is not only the rise of the independent software vendors, but Total particularly emphasized data independence, which I'll come to in a minute. And then we have a relational model of data from large shared data banks, which was an IBM internal research report in 1969, and was published as a ComACM paper in 1970 with a few revisions. And this came at the end of the 1960s. There are a number of other things, but we're now confined to an hour. We then had, during 70, 71, 72, the so-called Great Debate, which always makes me think of the Battle of Barnet. As you know, the Battle of Barnet was fought in the fog, and Warwick, the kingmaker, was run through and died. I wouldn't like to say who I'm going to cast in the role of Warwick the kingmaker, but it was a battle in an enormous fog, because a number of things had happened more or less at the same time. The Codicil Database Task Group report had been produced, which put forward the case for a certain type of product based on linking records, based on the so-called network model. IBM had IMS, which they didn't understand, because of course, if you were describing IMS now, you'd say, well, what your data structure is, it enables you to store complex objects with a hierarchical structure. That's how you describe it now. And one of the great sort of mysteries of IMS around that time is that it was marvelously successful in some contexts and a disastrous failure in other contexts. And the reason is now plain. It was because there was a confusion between hierarchies which are the result of access. I take a particular view when I access something. I start with a student. I go to the student's records. I go from the records to the classes. And I'm accessing via a hierarchy. But that hierarchy isn't natural. You can have other hierarchical views. Or you have natural hierarchies where the data is necessarily hierarchical. You have an insurance policy, and against an insurance policy, you have insured risks. The insured risks don't exist unless you have the policy. Beneath the insured risks, you have claims. You can't have claims unless you have insured risks. Against the claims, you have payments. You can't have payments unless you have claims, and so on. So therefore, you've got a dependent hierarchy, which is an access hierarchy, but granted, it's also a natural hierarchy. And there was that terrible muddle. Then, of course, there was Codd's relational model, which claimed to do all sorts of things. It almost certainly threw the baby out with the bathwater, in the sense that it produced such a simple data structure that there were large numbers of things you couldn't thereafter do except by acres of programming. But it was enthusiastically taken up by academics who couldn't recognize a baby at that time if they'd seen one. They had no understanding of data processing, so therefore they didn't understand what was being thrown out. So therefore this was a great debate in a great fog, and didn't really lead anywhere except to assist Bill and I in giving lots of kind courses, explaining what the problems were, and earning modest fees now and again, and enabling Chris Date to make a lot of money out of a book, and various things like that. So that was the kind of, that's the sort of battles. That's the battles of the 1960s, that's the dates. But what were the underlying ideas and motivations? Because, you know, you can't have a war and a battle and have lots of people being killed unless you have disagreement about something in the first place. So you've really got to have a kind of... so what were the underlying ideas and motivations? Well, they were different. There's no doubt that the motivations of Bachman, the people who did APL, were that they wanted better data structuring facilities than simple serial files and repeating groups within records, and simple serial files of records and repeating groups within records. They had the notion that you wanted to represent the data much more closely to the needs, to get data structures which would assist analysts and designers to structure files in a more useful way, that you could, as it were, go in and retrieve a record for a particular customer from the customer file. You could then automatically pick up from the order file all the orders from that customer. That kind of structuring. And that was one motivation, and of course with programming language features that enabled you to handle them. There was also the wish for data to be shared, although that to some extent came later. But in my view, the really driving motivation, and perhaps it's because of my kind of commercial activity with various companies at that time, was the idea of logical data independence. And it was very characteristic of large organizations in the late 1960s who had been early into computing, that they had data processing systems with large number of programs, you know, 120 different COBOL programs, and these 120 COBOL programs were variously accessing probably 15, 20 or more different files. And the whole lot was locked together and unmodifiable. If you wanted to modify the program, which caused you then to want to modify the record structure of a file, you then made the change to the file, you then modified the program, you then recompiled it, you then had to recompile all the other programs that access that, and inevitably it was very common, tremendous maintenance effort, and then the whole system would crash 6 months later because you'd forgotten some obscure thing. And I think certainly from my own personal experience, that seemed to be the really driving force for database management software. You interposed, and the object was to interpose database management software between the data as it was stored and the data as the program wished to view it. And once you did that, you could then, as it were, produce what was essentially a virtual file of some kind, which could remain stable, providing you modified the tables, which caused it to be materialized from the data that was actually stored. And of course, coming back to the question of hardware power, I remember vividly doing a consulting job for a firm of car importers around about that time, and their complaint was this, that they'd put in a database management software product so that they could not only run their batch programs, but they could also access the files directly through terminals. And their complaint was that the batch programs now took more than twice as long to run as the old COBOL programs that they'd replaced. So I went down there and I carefully explained to them how, well, of course they took twice as long to run because there's much more work to be done. You know, the data has to be transformed from its stored form and so on. They were quite content, and they upgraded their hardware and paid me a fee for explaining it. So, you know, that I believe was very, very important and was to do with throwing hardware power to give you greater flexibility. So that was a great, those in my view were the two main driving forces, the two main motivations. There were a number of sub-themes, what I call the dream sub-themes, that, you know, data should be accessible to the casual user at terminals. You know, someone wanders off the street and says, how many red-headed under 35 policyholders do we have that haven't had a claim in the last 5 years? That kind of thing. And then even more so, we went round the second loop. I say we went round the second loop. We talked about data as a source and integrating data to and so on. This took me way, way back to 1956, 57 when I first came into computing, when we talked about fully integrated systems and data only being entered once and so on. When I actually got to grips with it, I chucked all those ideas away and got down to implementing simple, straightforward systems. So that was the 1960s. We then move into the 1970s. There was a tremendous drive in the 1960s. There's no doubt about that. There was a tremendous drive in the 1960s. And I think the drive came primarily from the commercial users who had real problems with large systems using straightforward COBOL, which helped them to get the systems off the ground, but they ran into trouble. The 1970s was an interesting decade. What's the time, Tony? Are you going to let me know? Is there any way I can know?
You've only 40 minutes so far.
40 minutes so far, yes. The 1970s was an interesting decade. I mean, the codicil systems, 1972, 73, 74, 75, in the 1970s, gradually came to be used, as did IMS, as did Total, as did Adabas, and throughout the 1970s, and indeed well on into the 1980s, these systems came to be not only widely used, but they were also improved. And they did go some way to solving, or at least addressing, the two main problems. One of the things they did not solve was the problem of schema modification to a running system. And I certainly know of IMS systems in the city that are still running, and everyone knows they've got the wrong schema. If only they could change the schema, things would be much better. But they can't actually take them down or reorganize the data. So therefore, modification, you know, you had to do your analysis, you had to do your design, you set up your schema, and that was it. So although they succeeded in the two major problems of logical data independence and structuring, they then threw up a new problem, namely that you can't change your database design once you're flying. You're living with it, except in a modified way. Then, in the 1970s, IBM devoted a significant resources to trying to make the relational model actually work, to see whether the relational model could actually work. I mean, the relational model, what the relational model done is thrown away data structuring in the belief that thereby you could actually raise the level of programming. And there's no doubt that the relational model was really quite good at generating research into locking, the problem of sharing data, the problem of back-out recovery, because you had a simple model actually to work with. SQL was developed and it is now with us for better or worse. I had a modest little hand in that, how to make the predicate calculus first-order predicate calculus understandable to COBOL programmers. Then, of course, the other fascinating thing we had in the 1970s was the charge of the unemployed mathematicians. This was really quite fascinating. Relational database theory became a fashionable topic for research. We had normalization from third normal form to Boyce-Codd normal form, fourth normal form, the universal relation, fifth normal form, Armstrong's axioms, lossy joins, lossless joins, tableaus, and on and on. And there's a huge literature on this, which seems not to have contributed very much, except to add to people's CVs if they're in the academic world. They gradually became a smaller and smaller group talking to each other, and now, by and large, disappeared. But in relation to normalization theory, of course, it followed the 80-20 rule. 80% of the benefit came from the first 20% of the ideas, and the first 20% of the ideas was essentially second normal form and third normal form, which have become standard and readily understood, and they're one of those things that, well, you can't, once you understand it, you can't put yourself in the position of not understanding it. You know, it's so blindingly obvious. Many things are like that in life. I mean, I can never understand why people have this problem speaking English, for example. It seems perfectly straightforward to me. However, so that takes us through the 1970s, but much more than that happened in the 1970s, because there was, we'd had this battle in the fog at Barnet in the early 70s, 71, 72. We had the development of these products. We had IBM trying to make the relational systems work. We had all this rather irrelevant and elaborate mathematical theory. But we also, in the middle of the 1970s, we had something called the ANSI-Spark report. We had 3 schema architectures and models for the conceptual schema. Now, this is actually very interesting because what was happening is that the professional database community was in some way trying to extend its sphere of influence into what previously had been the province of systems analysis and design. I mean, when I designed my first COBOL files back in 1959, 1960, and my machine code files before that, I never had any doubt that each record represented a real-world entity, and that the fields in the record were storing the extensions of functions from that real-world entity. I mean, it seemed to me such an obvious way to store data that you took that as read. I thought of it that way, probably because by origin I'm a mathematician. But other systems analysts did that intuitively. And of course, that was the province of systems analysis and design. And what we were doing in the 1960s were providing programming tools which would in some way be useful to the systems analysts and designers. But once the normalization people got going, they said they extended the province of database not to providing database programming languages and software, but they extended it into semantic data modeling, into the idea of modeling the real world, which of course the systems analysts have been doing for a long time, albeit intuitively. And now we can start turning to some of the sheet music that already exists. If we have a discussion, I can show you that. I mean, that's a history I gave in 1984. I won't leave it up long because it might be different from what I've been saying tonight. But you see, when we get in the middle of the 1970s the free schema architecture, we get a view of the world like this. We say, well, and again, around about 1975, it became conventional at database conferences to represent the real world as a sort of cloud, and the individual users had their own little sort of cloud, their own perception of the world. And we then had the notion that each of these users should have their own external schema, that data was adjusted to fit that which they wanted to do. But that somehow these were mappings from some conceptual model of the real world. And when you've got that conceptual model of the real world, you then map that onto some kind of internal schema, and people will pejoratively say records, indexing, things like that, you know, software that people deal with. And then you have stored data underneath. So this came into being as a view of the world round about 1975. Indeed, in 1975 that was introduced. And then there was the notion that we've got this conceptual schema, very pompous term, conceptual schema. I've even heard it called, I believe people called it an ontological schema at one point in time. And you know all about ontology, about the Green Mountain. You know, how can we talk about the Golden Mountain? The Golden Mountain doesn't exist. I mean, Bertrand Russell, History of Western World. But you've got pictures like this. There was the real world and data models, and now what data models should we have? Should they be based on entities, relationships, attribute relationships, semantic net formalisms, and so on? And it was a very happy decade because if you were in on this little circuit, you travelled about having meetings, which normally took place in relatively pleasant places. I mean, I can remember one saying, why does the database community always meet on the Côte d'Azur in January and February? And I remember replying, well, you know, anyone who sort of went north in January or February deserves all they get. I mean, you can obviously think better in the sun is the real reason. So there were the IFTC2 meetings that talked about modelling and database description and database architecture, and there were many others of these. And I suppose something did emerge out of it. And I think it probably did, in the sense that on the basis of 20 years from profits to profits, 1975 should start showing the profits in 1995. Well, maybe. But that's where we were, and that's where we were through the 1970s. But then we come on to the 1980s. Now, the 1980s are slightly more fascinating. What's happening in the 1980s is that the products of the 70s continue. You've still got IMS systems running. There's still IDMS systems running. Total systems are kind of dying. Adabas has developed its own peculiar flavour with its language natural. We've got COBOL itself now at last in decline. But what we're having happening is that the relational systems, principally Oracle, DB2, SQLDS, Ingress, the others, these are developing 4GLs and front ends and so on. In my view, they're trying to develop at the top there, with their 4GLs, more than their substructure can bear, because the underlying model is inadequate. So, of course, what some of us are doing is now trying to do to produce and make happen ideas which really existed a long, long time ago. In 1972, I remember, there was a paper by Bracchi, Giampiero Bracchi from Milan, saying you don't want n- ary relations. Binary relations are adequate if you represent abstract objects explicitly internally, but not externally. Scheer-Nyssen was saying the same thing. Indeed, in 1976, myself and Scheer-Nyssen were the two invited speakers at the annual conference of the Italian Computer Society in Milan. And we had dinner with Bracchi in his flat, which is right by La Scala. And in 1976, we were talking about having database management systems that were based on binary relational models. And many of you will have seen the pictures which Bracchi, which Nyssen endlessly produces of things like Nyan, his binary relational schema, is overly elaborated, really over-elaborated notation. When I was looking through this sheet music, I found a slide. Which I used at a lecture in 1984. And I was amazed to see this slide. And this slide said that, well, this person, she appears to have had her head punched out. She's an NE user, and then there's an E user, and then there's an SE, and an SE, and an HE. Now, I haven't quite worked out, certainly in my writing, I haven't quite worked out what all these things are. I'm pretty certain that SE is something to do with software engineering, but I don't know. But you see, what it's actually saying is that if we use a binary relational model, we can integrate data and metadata. We can have a schema which doesn't distinguish between instances and types, but simply regards instances and types as objects both of the same kind, and that we can represent the data graphically by binary relational graphs, that we can map binary relational graphs to triple stores, that if we want more elaborate data models, we can map these to graphs, to binary relational graphs, and that we can create even more elaborate fourth generation things here. And all these ideas are very, very old. All these ideas are very, very old. Binary relational graphs to represent data were being talked about in 1972 by Bracchi, in 1974 by Abrial, in 1976 certainly by Scheer-Nyssen and myself. Mapping these to triple stores was being talked about by certainly Norman Winterbottom in 1978, and Peter Titman and some people whose names I can't remember earlier in the 1960s. Data models are endlessly elaborated. So there is indeed nothing new in current research. What current research is about is taking lots of good ideas that we didn't have the hardware power for 20 years ago and making them actually happen now. But they haven't happened yet. I'm now into my hour, am I, Tony?
You have 5 minutes to the hour to give you all the time for 10 minutes to go.
Right. In that case, let us move on to another theme, which is currently confusing matters enormously. about 10 years ago, Xerox PARC had a research project. And there was the notion of object-oriented programming. Now, I remember vividly John Quarantine coming rushing into my room, and it was 1981, and seizing my board and seizing it, and you know, John was explaining to me that object-oriented programming was the greatest thing since sliced bread. It was actually a new invention. What you were doing was mixing up your program with your data definition. Well, I said, oh yes, you mean like BCL? He said, what's BCL? I said, well, way back in 19, whenever it was, there was a language called ACL, which was a sort of COBOL language, and it was called the Atlas Commercial Language. And it was running at the University of London Computer Centre, which had the notion that they were going to make an enormous amount of money by using the spare time on the Atlas computer to sell time, and therefore they had to have a COBOL-like language. And one David Hendry created ACL, and he then got bored with that and created a new one because the first one was called ACL and it was called BCL. And that was an interesting language because you define COBOL records, and if you wanted any procedures within them, you put them in the COBOL records, and all of that worked. Anyway, so I said yes, but we'll give them that. It's brand new, it's object-oriented programming. And object-oriented became a buzzword. And object-oriented is now applied to everything. You have object-oriented analysis and design, object-oriented databases, object-oriented, well, you name it. And in fact, you have, I mean, you know, shades of lambda calculus here. You go lambda x, object-oriented x, applied to whatever it is, object-oriented x, where x. Now, the sources of confusion are really quite fascinating. And it's concerned with the word object, because if you look back at the database literature that I've been talking about, 1970s conceptual modeling, you'll find the word object and entity is used more or less synonymously. Indeed, some of the papers that you think are about entity modeling, if you actually go back and read them, you actually find they use the word object. The Smith papers on aggregation use the word object throughout. So, so object and entity have been used synonymously in many areas, but in programming they haven't. If you talk to programming language theorists, they like talking about objects, and when they talk about objects, they mean bit strings, they mean binary trees, they mean double length representation of real numbers. So that the word object has been used in programming theory as a generic term for a long time. And of course, when it came into object-oriented programming, naturally, what they were talking about was some piece of programming construct. And as you know, an object in Smalltalk or something is a piece of store with a number of slots, like a COBOL record, and you can have pointers and you can have variables. In other words, it's a very elaborate type of programming language terms. And what object-oriented programming is about is defining these very elaborate data types and defining chunks of code, methods, that work on them. However, so therefore, if you say to me object-oriented programming, I really do understand what you're talking about. But as far as other things are concerned, you know, your guess is as good as mine. So the sources of confusion are, we understand what programming language theorists mean by an object. It's a bit of store with some structure. Whereas in the database literature, the word object is used synonymously with entity. And some of us have probably experienced, I'm certain Bill has, course on object-oriented design. You know, you take out your lecture notes on entity modeling, and you take your text editor, you substitute entity for object, and you have a course on object. Right. So the word object has often been used in the literature on data modeling synonymously with entity to mean a distinct identifiable real-world thing. But the term complex object is also used now in the database research literature, because you've got to realise it's very important to understand what people don't understand in the database area. For example, you can read a lot in papers at the moment with things that say roughly this. They say, the relational model is very good for business and commercial applications, but it is no good for engineering applications. Right? What they need is complex objects, i.e. things like IMS records. Right? And they've never actually known that when you actually try and use the relational model in a commercial context, modelling is really quite difficult. And then, of course, we've got the other source of confusion, that oriented and orientation are all English words with a commonly understood meaning, whereas, of course, in object-oriented programming, object-oriented is a technical term which means what the object-oriented programming committee defined it to mean. So now we have an enormous confusion with object-oriented databases, I won't, I've got some nice slides on object-oriented programming. Do we want to make sure object-oriented programming? No. Right, so we'll move over those. But we now have the notion of object-oriented databases. Now, what on earth can this mean? What on earth can this mean? Well, I mentioned earlier, that during the 1980s, there is one important idea which has come into the database area, and that is the idea of persistence as in persistent programming. The importance of the idea is that what you're doing is you're effectively operating as though your database were entirely in memory. It isn't, of course. Your database sits out there on disk and is paged in as needed. But the paging in as needed is entirely hidden from you. It works, essentially, it's bringing the paging mechanisms of operating systems into databases. And that notion of persistence is very important. And of course, what object-oriented databases really are things like Gemstone that provide you with persistent small talk. Any of you who've used small talk know it's a fine programming language. Use it on your PC. Immediately you run out of memory, it goes bang, because it's an in-memory system. There's no way of storing any data. So you've got database management software now, so-called, that essentially things like Gemstone that provide persistent small talk, things like Ontos, which provide persistent C++, and these are consistent with the well-defined meaning of object-oriented programming. They are also used, we now use the term object-oriented databases to refer to extensions of relational databases to handle complex objects, which has got nothing to do with object-oriented programming, and proposals for databases to implement directly the semantic entity attribute relationship model. So what we have here is a kind of rerun of history. You know, what we've got is another battle in the fog at Barnet, except that it's now 1992. The Warwick of 1972 is dead, but the present Warwick is still fighting. I'm going on too long, Tony. Let's stop, and Bill can now correct me where I've gone wrong.
I think there was one thrust that was omitted. I'm sure, and I know Tom's giving a lecture now.
Yeah.
I think since you carried through from the 60s through to the 90s, I think one of the big thrusts in the 60s was that it was important to separate data and programming. In other words, you have this concept of a central database, and programs used it, but the central database was still there. Hence you have the separation. And that, I guess that was recognised sometime around 66, 67. The early database work, like Charlie Bufton's IDS, didn't have that thrust, but it was realised that you had to pull the two apart. And I think we've sort of had that. That's been a sort of common thread through all the various things you've talked about. The hierarchy, network, relational kind of big debate, and all through the conceptual schema. Nobody's ever questioned this business that data and programs should stay separate, because lots of programs want to use the same data, and some of the programs you couldn't even predict. Now we've got to this object-oriented lifestyle, and we're finding that they say, aha, yes, but you have to relate the method, so-called, with the data. And because most of the people that were saying that weren't around in 1965, they probably weren't born, most of them. And I find this somewhat ironic, that we've seen that kind of, what's the Italian, volta-faccia, something like that. We've seen this turn about.
But these are, really like database procedures.
Not really. No, I don't think so. I think they're more inherent. In the object-oriented approach, the fact that one bundles the method with the object, and we spent all these years, we didn't actually spend. It was very quickly recognised that burying data in programs was a bad idea. We used to do it. We used to do it in the late 50s and early 60s, and we realised that recompiling stuff just to change data, bad idea. Pull them apart. And now we see them going back together again, and I think it's rather ironic.
Yeah. The interesting thing about object-oriented programming, of course, is that the motivation claimed was code reuse. It was sort of a strongly notion that you get these objects, and therefore you had the notion of encapsulation. Now, I came across a fascinating paper which was buried in an Esprit project I was reviewing, which was entity attribute relationship modeling for object-oriented databases. And of course, this is important, because you see what you're doing is that if you've got an entity attribute relationship model and you're going to implement it in C++, say, then you're going to implement your entities as objects, you're going to implement your relationships as entities, as objects. You're going to try and represent your transactions as objects. And yes, the problem, of course, is that the notion that we should have encapsulation is anyway. You send the message 1 + 2, and then you make 3. Okay.
I think a common theme of this, certainly from my own experience, from my point of view, has been, as you so rightly say, that the ever-increasing power of hardware has allowed us to revisit a lot of the things which we had to give up because, although they were conceptually very nice, there was just no way they would run on the hardware available at the time. And I think that is it's something which, why I think it's quite useful to revisit history, because very often you can look back at things and you can find very key ideas which now their time has come, but they may have got forgotten.
Yes, there's several. The most interesting, there's 2 interesting ones. 1962, there's a paper, famous paper, not famous because nobody seems to know about it, a famous paper called Information Algebra, which incidentally, how can we put this? Well, in information algebra, you have the concept of bundling. And the concept of bundling is a generalization of the join of relational algebra as put forward by Codd. I personally do not believe that Codd had not read the information algebra paper, but he did not acknowledge it, and therefore claim the notion of join as an original thing, whereas it isn't. And I mean, if you look at what's her name, Jean Samet's book, a giant book on programming languages, published about 1970, she discusses, fascinatingly, she discusses in the same chapter, juxtaposed APL, not this APL, but the Iverson's programming language. She discusses APL and information algebra as important unimplemented concepts. Right. Now, do not blow my own trumpet. We've implemented information algebra in FDL very easily. So that's a very interesting one. I mean, and indeed, it also has in there the data model it uses is not a good data model, and the reason that the data model is not a good data model is it's exactly the same as the universal relation in relational algebra. In other words, you have a whole. In other words, your data model is the Cartesian product set of every value set you can lay your hands on. You find all your value sets, you form a Cartesian product set, and they're the points in space. So that paper now deserves revisiting because, according to Jean Samet, Bill may know them, but Bozak or people who
I
did,
met him once, yeah.
they vanished without trace in the early 60s.
It's actually the Conceptual Systems Committee
That's right.
that published it, but Bozak, he was essentially always recognised as Bozak's.
That's right, and I mean,
he was at somewhere in Los Angeles.
I mean, Jean Samet says, well, you know, they packed up and went away because no one had the earthly idea how to implement the thing.
Well,
and I mean,
they didn't know what to do with it.
Yeah, but you couldn't possibly have implemented it on the technology of that time, whereas now you can. The other fascinating paper, which one could have mentioned, is Feldman and Rovner's paper of 1968 on associative triples and doing inferences of triples. And there again, that was another sort of paper that you know, you could do very simple noddy things, but the sheer hardware power required to do anything significant simply wasn't there. But yes, you know, research, you should always say to research students, spend, you know, a couple of hours a week browsing old COM-ACMs I can remember, I mean, I showed a research student the other day, with rational about macro generators, and I realised that there's a macro generator in C which runs under Unix, under the Sun system, called M4 macro generator. And when I was looking at this, I realised that this was actually a crypt from Chris Strachey's macro generator. I mean, one of the most elegant papers that's ever appeared in the computer is Chris Strachey's GPM, which was published in. Anyway, so I did a copy of this paper and gave this to research students. Thought that M4 was something that had been invented in the last 5 years, because in common with most young people, everything's been invented in the last 10 years.
How?
I'm Gearing. I'm a mere statistician trained before the war, but I had the job of producing a sales information database for management, originally on punch cards. When anybody wanted an analysis, it took weeks to dig out the cards and sort them. And eventually, when we got onto the Orion computer from Paris Salmas, we managed to produce a system that could produce any sales analysis that was wanted for the past 5 years within 48 hours. And that technique is written up in a paper which I gave Gearing, Reynolds and Sears at the IFIC conference in Edinburgh in 1968. And you people who are experts in databases of nowadays, I'd be very grateful if you could spare time just to look back at that paper and say whether I really was setting up a database. I think I was. So I got all the information that management wanted. and the information that the Board of Trade wanted for its census of production, produced by basic Orion code written specifically in a high-level into a high-level system that users could merely put in a few parameters and select the tabulation of the form they wanted. And I'd be very grateful if as a specialist in databases, you could look back at that August 1968 paper that I fit by Gearing, Reynolds and Sears, and sometime tell me whether you think that it was worth marking as an archive.
I must have that somewhere actually, because that was a beautiful sunny week. At 1968.
It was in the supplementary papers.
Yes. But you actually there raised a point which one probably should have mentioned earlier. I mean, I've been using database in the sense of database management software, right, rather than as a collection of data. Right. Now, when the term database became fashionable in consequence of database management software, people then started to use the term database to mean collection of information. Interrelated data in some way, you see. So to them it would be totally baffling if I said to Bill, do you use a database system? And he says, no, we keep our data on VSAM files. So that we've always had this kind of confusion, and this has become worse confounded, I guess, in the PC world, where we have what are essentially file managers.
It was sales classified under 15 attributes.
Yes.
So any potential arrangement of those 15 attributes and the time base would be called for.
Yes.
So it's written out there in the paper. I'd be grateful for your opinion. It's 25 years or more ago, but...
Peter, it's worth asking you, I was fascinated, went through that review of those 30 years. Two words, data dictionary, never crossed your desk. Now that did surprise me, because I have a suspicion that you may have a claim to fame, which given that we're in a museum, you may like to put on record.
That's a different subject.
But closely
But they
related.
diverge.
Not unclosely. Look, if you look at this, that's actually a... That's actually a reproduction of the visual I used at the invited presentation in Milan in 1976, in which the data dictionary system. Now, why is this reproduced like this? Well, it's because a few weeks ago I was invited to give a presentation at the data manager at MSP, right, which produced Data Manager, and the reason was it was the 15th anniversary of me giving a previous presentation. The previous presentation was therefore in 1977, and that was the 10th anniversary of my original paper on data dictionaries. But that's a different theme. Yes, I mean. Well,
Peter, you can't have data independence without a data dictionary.
Oh, I agree with you. I agree with you. I agree with you. But
without data
I agree with
you
you.
don't have databases.
But when I was writing about data dictionaries in the 1960s, what one was talking about was providing a coherent form of documentation for essentially COBOL files, right? And the original products, the Arthur Anderson product, Lexicon, which was based on my paper, and Data Manager, which was then based on Lexicon, and I mean, some of you probably know David Gomez da Costa, who runs MSP. That was for the world of data processing, as it were, and it's the kind of systems analysis and design, the dictionaries and so on, which of course is my other interest of SSADM and Marie's and that kind of world. Now, I agree that they now do relate to database, but I wouldn't agree. I mean, whilst a data dictionary is necessary to database, you can have data dictionaries without them. I mean, if one was doing a system using vSAN files, right, if we were going to set up a system using vSAN files and COBOL, right, now, we'd use a data dictionary system and we'd use data manager.
Isn't the distinction there, Peter, that in fact the data dictionary of that early era was a compile type data dictionary, whereas in order to assist you in the integrity of the use of names and the naming of objects, naming of data sets and so on, whereas eventually that moved into the real-time interactive form of data dictionary that is actually used at runtime on the compiler.
No. Originally it had to do with system design. Right? Originally it had to do with system design. You had to design your records before you had to use them. But we're now going into a totally different world. We're now going into the world of kind of AD cycle and the IBM's information resource manager. IRDS.
Okay, right. Call time. Sorry.
Time to go for pizza.
Different subject.
Yeah.
I don't agree.
Well,
No, I mean...
it's a related subject, I agree.
No, I think it's very much the same subject, because I do believe that a dictionary, a modern dictionary, should be treated in the same way as we treat any collection of data. In other words, it should be represented as a database.
Oh, I agree with that.
So
but I mean, hang on.
talking about
Yes. But if Roger and I are implementing our system using vSAN files and COBOL, right? We use our data dictionary. Our data dictionary may be implemented using the database system. I agree with you, but that's just by that. But
I don't know. I think.
Okay, come on, right.
This is theology.
But the other interesting thing, one of the big differences between I was thinking about this when I was looking at the machines when I was coming in. If you're interested in old cars and you want to go on the rally to Brighton, you can't take your XR2 and convert it into a car for the purpose of going down to Brighton on the rally. Whereas the fascinating thing about computing is you actually can.
That's a nice note to end on, Peter. Thank you very much indeed for that talk. It was very interesting. Thank you.